Hi guys, my name is Kwang. I've been making videos going over college math courses. So we're gonna start out the first one with multivariable calculus. I hope you guys like it, and if you have a course that you would like me to make a video on, or if you have a question in particular that you would like me to answer, please let me know. Thank you. Alright, today we're going over vector calculus, and the first thing you learn in vector calculus is what a vector is. So let's get started with what a vector is. Alright, so there are two working definitions we'll be looking at. One is the one that commonly explained by a lot of people. When you say what a vector is, people say the vector is a quantity that has both magnitude and direction. Alright, so this is a good way to look at the vector. Unfortunately for me, this is not a good way to understand vector in terms of computation. The way I like to speak about vector is in real number. It's just number, right? You just have one entry. For vector, you have multiple entries of numbers. So another way to think about vector is a vector is a quantity with. Alright, so that's how I understand vector. What are examples? Example vectors are something like 1, 2, minus 1. In regular number, you just have number 1, number 2. If you combine them into one object, this is called a vector. Alright, it doesn't have to have 3 entries. It can have 2, it can have 4, it can have as many as you like. And the opposite of vector, which has multiple entries, we call it scalar. Right? So that's just some definition on what vector and what scalar are. Right, now that we have a new type of object called vector, we also want to know what can we do with it. For example, in numbers, we can get two numbers, we can add them. Pick two numbers and we can multiply them to do those operations for vectors too. The first two things that we'll learn is addition and multiplication by scalar. Alright, so when you have two vectors, and when you want to add 1, 2, 3 to another vector, these were the way that you would expect, meaning you add 1 to 2, you add 2 to minus 1, you add 3 to 4. So it's going to be 1 plus 2, going to be 2 minus 1, going to be 3 plus 4, and the final result is still a vector, going to be 3, 1, 7. We also can do multiplication, meaning if you have a vector 1, 2, 3, and you multiply it by a scalar, then what you get is you multiply that scalar to every entry in that vector. So the result would be 5, 10, 15. Alright, as I said at the beginning, when we think about vector, a lot of people like to think about vector as a quantity with magnitude and direction. So far, we just have a bunch of numbers. Where is the magnitude? Where is the direction? Well, let's talk about that. When you have two entries, this corresponds to xy plane. So to draw a vector in xy plane, the first coordinate will tell you how far you go horizontally. The second coordinate will tell you how far you go vertically. For example, to draw 1, 2, you say 1 means 1 step to the right, and 2 means 2 up. We go up is positive, we go to the right is positive, we go to the left is negative, we go down is negative. Right 1 step, we go up 2 steps. This is vector 1, 2. Likewise, if we want to draw a vector 3 minus 2, we do 3 right, 2 down, because the second coordinate has a minus sign, which means we're going down instead of going up. Without minus sign is number 2, which means we go 2 steps. Okay, this is 1, 2, 3 to the right, 2 down, mean this point. This is vector 3, 2, minus 2. Now that we have pictures of vectors, we should understand also how addition and scalar multiplication play roles in geometry of a vector. Alright, so what we like to think about adding vector geometrically is we do it head to tail. So for example, as before, this is vector 1, 2, right? And this is vector 3 minus 2. The way we think about adding these two vectors is we're going to translate one of the vectors so that the tail of one vector lands precisely on the head of the other one. So in this case, I'm going to translate 3 minus 2 so that the tail of 3 minus 2 lie on the tip of 1, 2. This and this will go like this. Right, so this is 3 minus 2, the same vector here, 3 minus 2. Right, and whatever you get as a result, meaning you start from 1, 2, you follow along the arrow, the final result will be the endpoint of our new vector. 1, 2 plus 3 minus 2, which gives us 4, 0. How about scalar multiplication? Scalar multiplication will scale the vector. So you get a new vector that point to the same direction or opposite direction, but have different length. So for example, if you do 1, 2 here, right, as before, we have 1, 2 is this vector. So if you do 3 times 1, 2, that will give you 3, 6. Right, so 1, 2, 3 horizontally, and 1, 2, 3, 4, 5, 6 vertically. So we end up at this point. The whole thing will be vector 3, 6 because you get 3, 6 from 1, 2 by multiplying the vector 1, 2 by 3. So we get 3, 6. Right? So these two vectors will be two vectors that point to the same direction but have different size. There's another way to represent vector, which is IJK notation. So you're going to write down I with funny arrow on top, J with funny arrow on top, and K with funny arrow on top. And the way it works is I will be the same as 1, 0, 0. J will be the same as 0, 1, 0. And K will be the same as 0, 0, 1. Right? And with this is kind of like your building blocks. With this T3 vector, you can achieve any vector you like. For example, if you want a vector 3, 5, minus 1, you realize that you can obtain 3, 5, minus 1 by multiplying 3 to I. You're going to get 3, 0, 0. Multiply 5 by J. You get 0, 5, 0. And multiply K by minus 1. You will get 0, 0, minus 1. And then you just add the result up. So the same as 3I plus 5J minus K. When it comes to how to construct a vector, there are several situations that you want to know how to construct a vector. But one situation in particular that it will come up over and over is how to construct a vector that starts at a particular point and end at a particular point. Right? So for example, on my xy plane, I might have something like 0.22, and I might have another point right here. So 2 minus 2, 3. And you might wonder, what if I want to start here and end up there? The formula is, if you want to go from P to Q, you do endpoint minus the starting point. So in this case, it will be Q minus P. Vector from is what? Is 2, 2 minus 2, 3. So it's going to be 4 minus 1. Alright, and this is a good place that you do reality check, right? Not every problem you have a chance to look at the answer and see if it makes sense, but this one you can totally do that. So the vector from 1, what is it? It's a vector that go 4 steps into the right, 1 step down. So if what you did is correct, at least what should happen is the result vector should be a vector that go to the right and go down, which makes sense. It's go to right and it's go down. Alright, now we want to generate a lot of vectors. Right? So far we just do one vector, two vectors, add them up, you get a third vector. Now we will have something that you can generate a bunch of points or a bunch of vectors, and those vectors will together form a line. That's what we call line equation. The form gonna be something like this. LT equal to is a vector on the line V is. Alright, so picture why it looks like this. If this is your line, what you need is two information. One is, can you find a vector or a point the line on? And on top of that, you need the direction of the line, which is something like this. This is V. Alright, once you figure out those two vectors, you combine them into equation like this, and this will be parameterization of your line. Alright, so let's do example. Alright, so one may ask you this kind of question. Find the equation of a line that contains vector 2, 5 and parallel to vector 1, 4. So when you're given problem like this, you're going to be asking yourself, do we have those two information that we want? Which means, do we have A, which is a point on the line, and do we have B, which is direction of the line? Of course, this tells you precisely that the line contains this point, so this is a point on the line or a vector on the line. The other information that we have is parallel to vector 1, 4. If a line parallel to this vector can be used as your direction. So A equal to 2, 5. LT would be given by 2, 5 plus T times 1, 4. And that's your answer. Alright, so one can ask you this question. Find a line that contains 1, 5 and 2 minus 2. Let's draw a little picture here. 1, 5 is right here. 2 minus 2 is right here. And of course, the line that we want kind of look like this. So of course, we want to use the same strategy, meaning we want to find a vector A, which is a vector on the line, and we want to find vector B, which is direction of the line. A come to you right away. In fact, we have two choices of A. We can use this as our A, or we can use this guy, right? You can do either one. You get slightly different answer at the end, but both will be correct answer. In this case, I'll just use 1, 5. The harder part would be what the direction of the line or the V is. But if you look at the picture and imagine what happened when we introduce the direction of the line, what you want is, you want any vector that kind of like point this way, right? And one possible vector is a vector that starts at this point and at this point, which we earlier talked about is just endpoint minus the starting point. B will be 2 minus 2 minus 1, 5, which gives us 1 minus 7. Just like A, is that it doesn't really matter which point you use. B also doesn't really matter which one you subtract from the other one. You can start here and end here, which means you do 2 minus 2 subtracted by 1, 5, or you can do it another way around. You get slightly different answer at the end, but both will be correct answer. LT will be 1, 5 plus T times 1 minus 7. We went over two problems that ask you to find lines. Now we have different type of problem that instead of asking you to find a line, they give you two lines. But the question is, do those two lines intersect? So this is something that's different from two-dimensional to three-dimensional. In two-dimensional, when we have two lines, if they're not parallel, then they must intersect somewhere. In three-dimensional, you have much more degree of freedom, meaning you can have a line and you can have another line that those two lines are no way parallel to each other, but they never intersect. So it's a common question to ask whether or not two lines intersect when you are in three-dimensional. The most common mistake is two lines intersect. We just equate them and solve for t, which is a mistake because the fact that these two intersect doesn't mean that they must use the same t. So what you should do is you plug in t for one and s for the other one, and then equate them. So equivalently, it's the same as asking, that are there any realization, meaning are there any t that when you plug into L1 you get a point will be the same as you plug in s, might be different from t into L2 and then you get the same point. All right, so from here we have 1 plus t 2 minus. All right, and when two vectors are the same, only when each coordinate are the same. So instead of have one equation that contain two vectors, you can have three equations. So 1 plus t equal to 2 minus s, 2 minus 2t equal to 5 minus 3s, 3 plus 2t equal to 1 plus s. Right, so what can we do about this? We will solve for s first by multiply this guy by 2, add to this guy, and the purpose is to get rid of t. So if we call this guy equation 1, this guy equation 2, we say 2 times 1, and then you add to 2, will give us what? 2, 1 plus t plus 2 minus 2t, twice of 2 minus s, plus 5 minus 5s. Right, so this is twice of equation 1 plus equation 2. The same will be the same as twice of equation 1 plus equation 2. And what we want to happen is we want this t to cancel. So 2t minus 2t, so these two cancel. Left hand side end up with 4. How about the right hand side? We have 4 minus 2s plus 5 minus 3s. Alright, so these 4 will cancel. Minus 2s minus 3s become minus 5s. Move to the other side, you have 5s equal to 5. So s equal to 1. Plug that in to 1. Then what we have is 1 plus t equal to 2 minus 1, which is 1. So t equal to 0. Right? So what we got so far is we said that if these three equations will be satisfied, it will satisfy at the point s equal to 1, t equal to 0. We haven't shown that it's satisfied yet. It might not satisfy, so we have to plug it in to check our work. Alright, so what you need to do is you just take these three equations and plug in s equal to 1 to t equal to 0 as we showed. Right? So the first equation will become 1 plus 0 equal to 2 minus 1. This is good. 2 minus 2 times 0 equal to 5 minus 3 times 1. The left hand side is 2, right hand side also 2, so this is good. The third one becomes 3 plus 0 equal to 1 plus 1, which is bad because the left hand side is 3, the right hand side is 2. Right? So conclusion is these two lines do not intersect. Right? And that will be the end of our review today. Next time we're gonna go over dot product and cross product.